Hello everyone, welcome back to the lecture series of numerical methods. In the previous videos, we have introduced a topic of numerical integration where we have covered trapezoidal and Simpson's rule. In this video, we are going to understand Gauss integration method. Firstly, when we have derived trapezoidal and Simpson's rules, and in both of these methods, the values of the function was given at equally spaced points of the interval. But Gauss derived a formula which uses the same number of functional values but with different spacing. The general form of Gaussian quadrature formula for integrating a function f over an interval a, b is usually given by the linear combination of wi's into f at particular points xi's, that is this equation number 1. Now understand what these values are. These wi's are the corresponding weights. These xi's are called Gaussian points or the points at which the function is evaluated, and n here is the number of points or we can say the order of the quadrature rule, and the goal is to choose the values of xi's and wi's in such a way that the approximation is exact for the polynomial. Here the weights and the corresponding Gaussian points are symmetrical with respect to the middle point of the given interval. We will understand this statement later. For now, we have to find the values of weights and corresponding Gaussian points. If we have n number of points, then there will be 2n unknowns in the equation number 1 which we have to find. So for a quadrature rule with n points, we need to determine both the weights and Gaussian points, and to find the values of these 2n unknowns we need 2n independent conditions, and these conditions will come from the requirement that the quadrature rule should be exact for the polynomial of degree up to 2n minus 1, which will ensure the exactness of the polynomial of degree up to 2n minus 1. Or in short, we can say there are 2n such polynomials, so we need 2n conditions to enforce exactness for these polynomials. So we will consider the f of x should be a polynomial of degree 2n minus 1. Let us mark this as equation number 2. Using the value of f of x from equation number 2 in equation number 1, it becomes integration from a to b f of x dx is approximately equals to integration from a to b c0 plus c1x plus c2 x square plus so on to c 2n minus 1 into x to the power 2n minus 1 dx. For the convenience, we will consider that the value of a here is minus 1 and b here is 1. So this integration will be equals to 2 times c0 plus c1 times x square by 2, but when we will put minus 1 and 1 in this will directly become 0. So omitting these values, the next term will be 2 by 3 into c2 plus 2 by 5 into plus so on. After that, we will put the value of x is equals to xi in equation number 2, and then we will substitute these values in equation number 1. This process will be very lengthy if we will consider the general terms, but for the understanding we will consider the value of n as 2 only. So deriving the Gauss form for n is equals to 2. For n is equals to 2, the integration minus 1 to 1 f of x dx will be equals to w1 into f of x1 plus w2 into f of x2. Here we have the n value as 2 and we have 4 unknowns. To find the values of these 4 unknowns, we must have 4 independent equations. So for that, on the similar lines, we will let the f of x here is c0 plus c1 into x plus c2 into x square plus c3 into x to the power 3. And here you can consider the maximum power of this polynomial is 2 into 2 minus 1, which is 2n minus 1. Now integrating this f of x from minus 1 to 1, this will be equals to 2 times c0 plus 2 by 3 times c2. Let us mark this as equation number 1, this as equation number 2, and this as equation number 3. Now carefully understand, putting the value of x as xi in equation number 2, it will become f of xi is equals to c0 plus c1 xi plus c2 into xi square plus c3 into xi cube, where the value of I here will be 1 and 2 only. Now substituting these values in equation number 1, that is integration from minus 1 to 1 f of x dx will be equals to w1 into f of x1, whose value will be c0 plus c1 into x1 plus c2 into x1 square plus c3 into x1 cube plus w2 into c0 plus c1 x2 c2 x2 square plus c3 x2 cube. Let us mark this as equation number 4. Now carefully look at equation number 3 and equation number 4. The left hand side of equation number 3 and 4 are same, so these equations are comparable. Therefore 2 times C naught plus 2 by 3 times C2 will be equals to, the coefficient of C naught will be W1 plus W2. The coefficient of C1 will be X1 W1 plus X2 W2 plus the coefficient of C2 will be W1 X1 square plus W2 into X2 square plus C3 into W1 X1 cube plus W2 into X2 cube. Now comparing these values, the coefficient of C0 is W1 plus W2 and in the left hand side the coefficient is 2. Therefore W1 plus W2 is equals to 2 here, and coefficient of C1 here is this, but in the left hand side there is no C1. It means X1 W1 plus X2 into W2 will be equals to 0. Similarly, the coefficient of C2 here is this, and in the left hand side the coefficient of C2 is 2 by 3. It means X1 square into W1 plus X2 square into W2 is equals to 2 by 3, and there is no C3 on left hand side, implies W1 into X1 cube plus W2 into X2 cube is equals to 0. Now we have to solve these equations and obtain the values of Wi's and Xi's. The value of W1 will be equals to W2, which will be 1, and the corresponding X1 value will be minus 1 upon root 3, and X2 value will be 1 upon root 3. Hence, the Gauss formula for n is equals to 2 is integration from minus 1 to 1 f of x into dx is equals to f of minus 1 by root 3 plus f of 1 by root 3, which will give the correct value of the integration f of x in the range minus 1 to 1 for any function up to the third order. This equation is also known as Gauss Legendre formula. Similarly, we can find the Gauss formula when we will take the value of n is equals to 3. On the similar lines, the Gauss formula for n is equals to 3 will be derived, and I am skipping the proof here and directly write the Gaussian formula. Now that we have derived the Gauss formula for the value of n is equals to 2 and n is equals to 3, and in the starting of this proof I have stated that Wi's and Xi's are symmetric with respect to the midpoint of the interval. Let us understand this form first. Symmetry of quadrature points, which is Xi's, when the interval of integration is minus 1 to 1. These points will be symmetrically distributed around 0. As we can see that when n value is 2, xi value is minus 1 by root 3 and the other point is 1 by root 3. Similarly, when the value of n is 3, the one point is minus root 3 by root 5 and the other is positive root 3 by root 5, which are symmetric about point 0. Or we can say that xi value is equals to minus of x of j value. And when the value of n is 2, we have only 2 points, x1 and x2. In that case, both of these points will be symmetric about point 0. But when the value of n is equals to 3, we can have only 2 symmetric point about 0 and 1 point will be left alone, which is 0 here. Why this point is 0? Because we have to maintain a symmetry about minus 1 and 1, and we have to consider that point which is symmetric about 0, and there is no other point than 0 which hold that property. Now let us talk about the symmetry of the weights Wi. The weights Wi are associated with these points are equal for symmetrically spaced points, which means the weights corresponding to symmetrically placed points are same. As we can see, when value of n is 2, we have 2 symmetric points, and corresponding that symmetric points, the weights are equal. Similarly, when the value of n is equals to 3, the weight corresponding to the symmetric points is same. But for the value of xi as 0, there is different weight here. So when the value of n is equals to 2, the weights w1 and w2 are equal, which reflects the symmetry of the quadrature points. I hope you have made an understanding of this statement, and in the next lecture we will try to do some practice questions based on this method. And if you have any doubt regarding the proof of this method, do let me know in the comment sections. And if my videos are helping you, then show some love to my videos and don't forget to share it with your friends. Happy learning!